Let me go through on a set of challenges that came up from this overall project. One is the information architecture, the other one is design flow and integration of a design flow, and the third one is the semantics and the integration of semantics for this. So as you see, the problem with the information architecture is that even if you, it's conceptual, you can imagine that that there are many tools that needs to be touched on while you are walking through on the design flow. And these many tools cover a very heterogeneous suite of models. In the physical domain, you are facing the following dimensions. Of course, the hierarchical decomposition, components, subassemblies, assemblies, full system level, and related to every one of these levels, you would feel justified to collapse the models and to create an appropriate new component model on the higher level. So certainly there is the hierarchical decomposition level, then the model abstraction levels, where the modeling abstractions also span a large space from untimed static characteristics, long parameter dynamics, and finite element methods. And then there are different physics domains, the electrical, hydraulic, mechanical, and so forth. And of course, ultimately, if there is a hope for model-based design, in a sense that you can develop the predictive capabilities with these models that are needed in the wholesale application of model and components-based methods, then one thing from which you can hope salvation, that you can interlink these traditionally isolated design concerns, and you can understand how they are interrelated and explicitly model them. Because that's where a lot of reserve exists, right? It's very common these days that the classical design flows have these different isolated islands of analysis, but these many interactions that kill you. So what the hope here is that you can somehow cover this broader space, but not only point-wise, but also represent the interactions across. So that's the challenge. And of course, if you go to the cyber part, the software part, you have the same story. You have the hierarchical decomposition, the behavioral abstraction layers, refinement layers, and there the similar kind of arguments can be told. But again, if you solve somehow the key challenge, how to span these very wide range of modeling domains and how to express the cross-domain interactions, then you can win a lot. So that's the ultimate hypothesis. Now, that kind of heterogeneity and the challenges related to this is true not only in terms of these different modeling domains, but also if you look at the overall program, how these different parts have to communicate with each other. So just look at that. The model library communicates with the vehicle forge, and through that with the designers through the component models. You have to have a reasonably lumped together and precisely defined component model that can cover all of these domains. When you look at the competition and how the competition coordination needs to deal with the designers through the vehicle forge, then comes another set of information, the requirements, the test benches that are linked to the requirements, the seed designs, I will talk about that particular thing, and the scores. So to put it in another way, when a designer steps into the space, the first thing what they need to do is to understand the requirements. The requirements are expressed in test benches. They get the so-called golden test benches. They can play with it, they can understand, they analyze it. These are the test suites against which their designs will be evaluated. These test bench models are essential for the designer to understand against what they have to do the design. They also need to deal with this whole other concept, which is the initial design. So, just briefly, when we started up the competition, or that before there was a beta testing phase, almost everyone was completely paralyzed. How can I start up that whole thing? Because there are too many tools, too many design concerns, too many everything. So it came out quite fast that the most effective path for the designer is to provide them seed design. The seed design is a working example for the whole system, let's say for the whole powertrain. That seed design then can be used for understanding in how, in that context, designs are working. They can run the seed designs on the test benches, run evaluations, and then they can start thinking about their own design as a refinement, changes to the seed design. We found everywhere that without that concept, the whole thing is just about useless. Ultimately, you can phrase it that way, that this whole infrastructure, what you see here, is and should not be considered as a snapshot for solving a particular design problem. This needs to be considered as an evolving knowledge base for creating designs. So indeed, this Vehicle Forge and the repositories behind Vehicle Forge that capture the design experience, that capture what were the evaluations on test benches against different parts in the design space, are awfully valuable to accumulate the knowledge for understanding how the designs in this whole category of problems look like. The design space is one manifestation of that. Design space is a good architecture, what someone tested, stumbled across, and presents it. It can direct totally the designer's attention in a wrong direction. But in the same time, if you don't do that, then it just total paralysis. So the hope was that people getting the seed design will be able to experiment and come up with different designs, which is relatively far from the seed design, which behave better. So that was one of the big hypotheses. Now it turned out that indeed, in the competition what we finished this April for the powertrain, the winning design team diverted good enough from the seed design. So they stumbled across some interesting solution. But broadly, it fall in the same general category of solutions that the seed design represented. But that doesn't matter, because if this is operated for years, then obviously the design space will be more and more covered, and particularly if you do it in a crowdsourced way, then anything can happen. Also, it's a quite interesting point for this connection that all of the designs were graded automatically. So the designers submitted their design. They could submit one design per day, and for the next morning, usually they submitted them late night, but in a few hours they got back the score. And that required that there is automation behind that the designs can be automatically run against the suite of test benches, and then the scores are automatically done and coming back. So that's also a non-trivial amount of information flow between these components. But you can do it for all of the others. Obviously, the Vehicle Forge, when it talks to the Open Meta tool suite, again, components, designs, design spaces, test bench models are all interesting. The competitors, in addition, they need to know also use cases, elements of the design. So we call them design vignettes and design threads. And finally, there is this whole mysterious interface between the foundry and the design flow. That interface captures things such as, if I have a design which points toward components, what will be the cost of the manufacturing, and what will be the lead time for the manufacturing? The second is that if you manufacture and build the component, how the certain parameters of the models in the models will change as a result of it. We are not doing too well with this. That's more and more coming up now. But we already have the good interfaces between the foundry and the design tools related to the cost and the lead time, which means that it can be factored in the design space exploration. Altogether, what you see here, that for that kind of communication across these different components, a lot of information needs to be packaged and sent around. So how can we solve that? The information architecture needs to deal with creating some kind of shared conceptualization, at least in this program. That program included all together with other places where what we didn't do, several hundred people. So there has to be a shared conceptualization formed. We need to find the semantically sound modeling languages that cover this space. And of course, we need to solve also the integration of the roughly 40 major tools that are impacted and used in the design flow, together with their modeling languages that they represent. Now, if you look at that challenge, depending on the community where you are, so I came from the domain-specific languages community. For us, the information architecture means that you define the domain-specific modeling language. How you define it? You design the conceptualization, you select the concept, you select the relationship across the concept and well-formedness rules, and you define the semantics for the language. That's easy. Of course, there are a lot of things to be done with that, but you somehow feel that when I'm a domain-specific modeling language designer, that's my own damn business to define for a particular design area my own domain-specific modeling language. But unfortunately, the shared conceptualization changes a lot of things, because it's not only your responsibility to make a decision how I conceptualize this overall design process. It influences a lot of other people who needs to share this. So it turned out that this shared conceptualization, which is actually the name for ontologies, is getting a first-order problem. It emerged in the problem to a good extent because Joseph drove us into this. And it emerged in the program such that at a certain point, about a year ago, 1.5 years ago, we had to create a task force which covered all of the groups and started working on this ontology set and defined basically an accepted set of vocabularies that was introduced. The other part of it is, of course, the integration of the creation of the modeling languages. But what's important is that for the overall semantic domain, there are these two directions. This is the so-called epistemic semantic direction, right, which is what things are, and this is the modeling language part, and which is how I'm doing things, kind of stuff. And these are interrelated because this shared conceptualization has to be used in the modeling languages you formulate. So that defined the boundaries for creating the information architecture. Now, related to the vocabularies, that was a torturous path because, first of all, we couldn't find standards. One would expect that vehicle design must have defined standards for ontologies that are used here. No, we couldn't find it. So ultimately what happened is that we started growing, evolving vocabularies. We grabbed vocabularies from the design tools, for example, from Modelica libraries. And we extracted vocabularies from the component model developers' terminology. We cleaned them up and got it accepted. So it was a non-trivial amount of work to establish an initial set of vocabularies and understand the fact that these will evolve and that will change. And of course, as I mentioned, the third element, to adopt vocabularies from used tools in the program is also essential. Modeling languages. The program started up with the intention that we will define a new modeling language for Meta. That was very fast given up. And it was given up because it would have been a daunting task, and at the end of it, no one would use it. The other thing is choose one that already exists and broad enough to cover the whole design space. We couldn't find that one. Of course, in these cases, things like SysML and so forth come up, which declares that they can be used for everything, but in the same time, they are good because they don't have semantics. So in that sense, they can cover everything. But if you really look the practicality for this, that's not available. So ultimately, what we end up with is a solution which was pragmatic and primarily accepted the fact that the modeling languages used in the program will be dictated by the tools, by the dominant tools that are bringing the models. And there is a degree of freedom what you can put to it, in which you can express your own suite of abstractions that the nature of the program requires, but the pressures to adopt existing modeling languages is substantial. This is the concept what we finally ended up with. Again, as I mentioned, we had about 40 tools that are really complicated tools like Modelica, ProE, Diamora, Delta 3D, so many different massive tool suites that impose you different modeling concepts and modeling languages. It would have been totally impossible to tell that the modeling language for the overall open meta is nothing else than the integration of all of these modeling languages. But it's possible to tell that I'm really not interested in all of the details of the modeling languages of these tools. From the overall integration point of view, what I'm interested in, how these different models have to interact with each other. Now, we defined for the meta, the AVM component model, where the AVM component model declared what is the standard way for model interactions. For example, physical interactions are going through the physical interfaces, which is an acausal interface with a standardized set of concepts, standardized set of variables, units, everything. So that's a fully specified set of interface. We are not interested in that sense, what is the detailed Modelica semantics, but we are interested how to map this standard set of physical interaction interfaces into Modelica. But it can be not only Modelica, but it can be also bond graphs or other physical modeling tools. So ultimately, it means that we built up a suite of so-called semantic interfaces driven by the specification of the AVM component model. And these semantic interfaces represented the different modeling tools' footprint for the model integration. It's a subset of the overall semantics of the tools, but it's semantically sound, much simpler, and it captures only those concepts what we needed for expressing the interactions. With this, we created a space what we call the model integration language space. That's the name of the name we use is sci-fi. We basically defined these semantic interfaces for these different model types and added those additional constructs that are needed for linking together these different modeling concepts. So altogether, the key element, the key new element in Meta, from modeling language point of view, is the particular model integration language what we use for linking together these different models. It's also clear that from the definition of this, it's obvious that it's evolving. It will never fixed, because as you bring in new modeling concern, it needs to be upgraded, changed, which creates, of course, another additional pressure, which is what to do with the semantics, because you cannot just do a gentleman agreement about the semantics. You have to continuously keep it tracked and formally represented. And that created a pressure to deal with this so-called semantic integration, which is provide formalized semantics for the model integration language and the mapping of the model integration language constructs into the existing tools. And that whole right column is dealing with introducing that concept, what we use for the semantic integration, and there is a formal language, what we use there, formula, which is coming from Microsoft Research, that provides a rich enough infrastructure for doing formal semantic specifications. And other arguments here, just briefly, why the model integrated language concept was convenient for us. Because it's a changing language, you had to have an infrastructure, a tool infrastructure, which can support changing languages. We have one of these tool infrastructures, which is called model integrated computing infrastructure. That's the nicest product what we developed in the last 15, 20 years. And that has a suite of meta-programmable tools that you define meta-models, so-called meta-models that are models of modeling languages, and these meta-models can transform the different tool components, the model builders, transformers, and so forth, to different domains very easily, inexpensively. So we are not forced to use one or the other's available standard tools. So altogether, we ended up with a overall open meta information architecture, which included a suite of ontologies and included a number of modeling languages, where these modeling languages or came from tools or were the evolving modeling language was defined for model integration. And there were some special purpose modeling languages, such as the test bench integration language and so forth, that we used as a more standard fixtures of the overall tool integration platform. Here is the summary of the information architecture. Ultimately, we use a model integration language. We use meta-programmable tools. And as a consequence of this concept, we use a semantic integration backbone, which means that a part of the overall story is the underlying explicit representation of the underlying semantics. Let me go to the design flow integration challenge. So this is the conceptual design flow. That the only thing what it captures is that it's a progressive deepening in the design and down selecting, narrowing the design space continuously in the process. Fortunately, I was already talked about the related big questions that that design flow leaves open these issues. How to start the design process, how to help its convergence to a good enough design which satisfies the requirements, and then how to manage linking together all of the tools. This is a more refined version of the design flow. Let me just briefly walk through on it. So right now, the overall design process starts with the seed design. The seed design is a particular kind of component assembly, but we pre-tested that it's working, and the designers can start with it and learn about the system. They can run on the seed design all of the test benches, and they can understand the overall problem with this. After this, they are progressing toward the whole design space issue. They start turning the original seed design into a design space by introducing parameters that they want to open up for optimization, and they can select also component alternatives from the component library. With this, they can enrich the original design into a design space, and they can expand it as they wish, as they are satisfied with the overall progress. After this, they start working on the design space. How they work on the design space? They start defining constraints over the design space. Compatibility constraints, such as they figure it out that it's not good to have seven wheels in one side of the vehicle and 4 on the other side of the vehicle. So they start introducing these architectural constraints, partially coming from the logic of the problem, partially their own taste. That's a creative process. They start generating configurations. They trim the design space against these constraints. After they went through on that static sequence of design space pruning step, they go into running the test benches. The test benches are the more complicated requirement evaluation processes. These are usually simulation-based. They run dynamic simulation, and they measure basically key performance parameters. These test benches cover, again, lump parameter dynamics, calculation even, static parameters, but they can include CAD and CAD-related characteristics. Now, in this step, they can also create new test benches if they wish, if they have an insight. They have the tools with which they can build additional test benches. They can define their own collateral or secondary derived requirements. After this, when they run these test benches, the test benches, you can imagine that they generate a huge number of simulation results. These results needs to be processed and used for the so-called parametric exploration. The parametric exploration means that they will have different visualization tools with which they can represent how the design space looks like, how the performance space looks like, and they can do optimization, use design of experiments method, and they can progress toward selecting and pruning further down the design space only those subsets that are performing well. All of these steps which relate to parameter explorations are represented on a dashboard, the design dashboard. I will show briefly some examples for it. These dashboards are really nice graphical representation of these parameter spaces with which they can do these optimizations, and then they go back and refine the constraints and iterate over this process. So that's ultimately the flow what emerged during the experiments.
Just a short question.
Yeah.
The test benches are commonly open loop test benches or closed loop test benches?
So they are open loop in a sense that the only thing what they do, you define you give the test bench a design space ultimately, and the test benches run all points in the design space, but they don't do feedback in that. They just the feedback is closed through the dashboard where it's visualized what coming out of it. And then the designer, I will show you, the designer can play tricks with, according to their preference and so forth, how to select solutions. Now, in this overall process, there is a critical component, what controls from tool point of view of the process is the open model composers. These composers are ultimately a bunch of model transformers. These model transformers are, as I described, we start with the seed designs and the design spaces, and basically the name of the game is to evolve these design spaces. It's all evolved such that the design spaces are given to the test benches. The test benches are running. The test benches are typically executable large simulations. But when you give a design space to these test benches, the executable simulation needs to be fully generated. It needs to be synthesized from the architecture specifications. And these meta composers do that. So they do the composition of the many different kind of models according to the nature of the test bench which is created. They run the simulation, calculate the key performance parameters, and it goes back into through the manual selection process to the design space evolution. This is a test bench model. This is a visualization of how the test bench models look like, and this is the bunch of things around it, and this is basically a design space specification that are named and represent a large number of points. Here is a list what they can see, what are the available test benches. We have about 70 test benches in the powertrain against which the different designs are evaluated. And it's I don't want to waste too much time for this. So there are many different kind of test benches and integrated tools. This is an example for this dashboard, which is used for visualizing after running a test bench against a design space. All of these vertical lines are individual key performance parameters. One color line here, what you can map here along, is one design point. So how they can use it, that they tell that for these key performance parameters, I want to select this range. When you select this range, that all of the other trajectories will be suppressed, and only those designs that are falling in this range, in these key performance parameters, are staying. But of course they are spreading. So they can adjust these parameter ranges individually, and they down select all of those point designs that are meeting their preferences according to different performance parameters. It's a multi-objective design process, so it's a very important thing to facilitate how to look at the different design objectives and balance out across them. This is for the parity optimization, a bunch of generated diagrams. These are also dashboard figures for the uncertainty propagation and the probabilistic certificates that are generated. So there are many of these things, and finally this is a generated 3D model, that an example which came out from one of the competitors. Okay. Now. The final point, which is, because I always leave that to the last thing, and it's always shortchanged. This is the semantic integration challenge, and what to do with the overall semantics. Why semantics is so important can be easily illustrated in this figure, which is the different models and representation related just to lump parameter dynamics. Here are the tools and model types what we consider to use. Simulating state flow, there is an embedded software modeling tool. This is, I didn't put the name of it, but we have a name for it. Hybrid bond graph, Modelica, True Time, I'm sure that you are aware of it, and of course the functional mockup units. So these are the different model types what we want to use and compose when we do lump parameter dynamics. I talked about what is the semantic integration layer, which pulls them together and allows us that, let's see, we can compose models or component models that for the behavior is specified in bond graph with another component where the behavior is specified with Modelica. Now, when you do the semantic integration and you generate stuff out of the integrated component models, what kind of things you need? One is you need to generate equations. Equations are needed because the verification tools, or some of the verification tools that are used in the program, requires equation specification of the dynamics. So we have to have a set of composers that from the models, the Modelica models, and particularly the Modelica models and the bond graph models, are able to generate the appropriate equation sets. These composers that are ultimately model translators are semantically involved. So you have to describe what they are doing. It's not enough to tell that the production toolchain have a C++ code which generates these equations. You have to specify what is it. Similarly, there are other groups of things that can be generated. One is when you want to do the integration not on equation level using basically denotational semantic, but you want to generate using these functional mockup units, the precompiled pieces of codes from which you can build a simulation. And finally, there is another layer in the simulation what we use, which is for distributed simulations. The distributed simulations are running on the HLA, the high-level architecture platform, which requires another set of generated code. So you can imagine that in a heterogeneous language environment with many different kind of artifacts that needs to be generated, you will have typically a bunch of different kind of models and a bunch of different composers or model translators that you need to use. So based on that, this is what we mean by semantic integration. So let's assume that you have a simple dynamics which has two electrical circuits linked together in ports with two wires. It's a physical component structure, and that's what we need to deal with. In the meta world, what you can do is that you put these electrical circuit components into the so-called sci-fi components or AVM components. And one of them can be represented in bond graph because it came from a library with bond graphs, and the other one possibly was represented in Modelica. Which is common in these two things is that there is a sci-fi component specification. We know what is this link. These are acausal links with appropriately selected physical variable pairs. Okay? And there is internally in the component a mapping which map these standard AVM component model interface points into the internal guts of these individual behavioral models. That red thing, so the component model interfaces, the links between them, that defines the architecture, what we created, and what you see here in physical sense. From this architecture, we need to synthesize, let's say, an executable simulation, or let's say, I want to synthesize both a simulation, both a set of equations that verification tools need. What do I need here? I need to take the bond graph model and translate it, let's say, into Modelica, because Modelica is an equation-based modeler. So there is a bond graph to Modelica translator. I need to take then the sci-fi component architecture model and translate that into another set of equations, because as you know, when you do physical modeling and physical interaction modeling, the physical connections are mapped into basically constraints, right? Other equations. You take these two models, that the Modelica equation models that are coming here, the sci-fi structure model, which is again is a equation, and you put into the composer. That composer takes all of these constituent models and generates the equation set. So that's actually almost literally what happens. But obviously there's a bunch of these kind of things. To make it maintainable and understand what's going on in a larger set, you have to have explicit semantic representation for what these things are. So you have to have a specification for the bond graph model and how the bond graph model shows up in these interfaces. You have to have a semantic specification for this translator and all of these for this composer and the mapping between them. So that's where we use the formal semantics and formula. That language you can look up in Microsoft Research Formula. That's again an open source tool. And that whole structure, what we call semantic integration. So it's basically an obligation that the modeling languages, the composers, have an explicitly represented formal semantics. Okay, I think that I better go to the end of it. Some experience related to the Fang 1 competition. So that power train competition was running between January 15th and April 15. It was quite an experience for us. There were 1,050 people registered, 268 teams were formed, and we structured the competition such that there were gateways that has to be passed that someone gets to the next stage, simply because there was a lot of handholding, obviously, so that we had to run a phone service and so a help desk and so forth. So 39 teams passed the tutorial gateway sequence. So they showed evidence that they understand the tools, they can run test benches, they can build verifiable models. 18 teams remained for the more sophisticated suite of design paths. And by about end of February, we have 13 finalist teams. One team was selected for a $1 million prize at the end of April, and that was a 3-person team who beat up basically 30-person teams, which was quite interesting itself. So in that sense, that was a good indication for us that this process in itself is the democratization of design concept is start evolving because individuals without any huge budget could do that design reasonably effectively. We continuously operated a test bench suite, so they saw the team saw how the test benches are running. What are the test bench, what was evaluated for them passed, what were the best, and what are the test benches that are failed. We operated a dashboard basically that showed continuously the current standing of the competition. Those are the team names and those are the scores of the teams. And here are some examples for the different kind of designs. Altogether, there were roughly 15,400 simulation jobs that were submitted for the evaluations. It was running on these cloud-based platforms, what we set up. And here is some scaling data which shows the complexity of the models. A typical size models in the full design has component numbers which reach 1,600, 14,800 variables, 300 constraints, 5,200 parameters, many unknowns, and so forth. So it was a reasonably complicated models. Right now we are working on the hull design part and the preparation of the design context for the hull design, and our teams are really running now or helping now the beta testers who are preparing for it, and the competition will be early next year. So summary. If we look the current limits for correct by construction design using this whole model-based process and model-based verifications, obviously scalability is still a main issue. You cannot expect that tools like Modelica compilers and even the best tools can just routinely scale up. Composition means that you can very easily create gigantic models, because semantically correctly you compose these things, glue them together, and very easy end up with model sizes that the tools are just totally unable to handle. So there has to be a lot of work going on how to change the fidelity level of the different constituent models such that it keeps the complexity under control. Verification tools don't scale, and certainly there is a fundamental problem, particularly in physical systems, that if you want to have if you want to have any kind of scalability, you need to use abstractions that the verification tools can deal with, so they are scalable, such as linear dynamics. But if you use linear dynamics, you lose the relationship with the physical reality. You create this mysterious epistemic gap. You don't know what you don't know, what you miss there, right? So it means that you really don't understand how to interpret the result of the verification, because at the end of the day you verify the model and not the system. So that's certainly a nagging problem how to handle this issue. Certainly we are now in the process which is understanding how good the model libraries were. The build system produces now the measurement results, and we have another spiral to refine the model libraries and try to do some kind of validation for the used model libraries, and that's a quite interesting process. So altogether, it's an interesting effort, certainly, and it got a taste for many of the researchers who are involved in the program. What is reality? Regarding the short-term output, DARPA made an agreement with NSF that through the NSF CPS virtual organization, the tools will be made available, and there are different challenge problems that are created that are derivatives of this program. So hopefully that will come on board next year, and it will be more broadly available for the research community. Thank you very much.
We have time for questions. Questions? Yes.
Very much. So I'm quite interested in the scalability issues you mentioned. So do you have more like specific per tool or per semantics account of where the main scalability problems arise? Is it more in the verification tools or cogeneration or on the modelica side or more discrete?
Yeah, it's simulation and verification. So there are scalability problems with modelica tools. It's very easy to build compositionally large enough models that, for example, Daimler cannot handle. Where anomalies happens that you change the position of two lines in the equation set, and in one case the model is simulatable, in the other case the model is not simulatable. So you very easily hit that point that the separation between the models and the simulation tools disappears. So you have to adjust the models for a particular kind of simulation tool. So that's obviously it's not a good place to be.
Yeah, this is quite, I guess, common for verification, but for simulation, it's a surprise. Yeah.
It's just a matter of how far you go with the model sizes. In verification, verification, the problem is that many of the, if you ask folks who are building the physics models that how would they want to create simplified models or low fidelity models, for them the trivial thing is not that I use a simpler abstraction. For example, I change to linear dynamics. They will still use nonlinear dynamics, but they scale back the number of the interactions that they want to model, but it still remains nonlinear. And obviously the verification tools are chronically badly behaving for these kind of systems. So the field is littered with these kind of problems. And actually the message is that that it's really a good agenda to think about how to make all of these technologies relevant for real life problems. And certainly what would be very helpful to make these type of test beds available for testing, for doing real life testing of different ideas.
Yes, then Michael.
Thank you very much for the presentation, first of all. I mean, you explained a lot with the physical side of cyber-physical design, but I was missing a little bit of the cyber part. What type of tools and modeling languages are you supporting for embedded system design? That's the first question. Also related to it, is it supported or planned to be supported some sort of hardware software co-design in this?
Yes, it is. We already have a tool suite in the tool chain, just it was not heavily exposed because the powertrain and now the hull is so much physical. And the other thing is that we had plenty of experience with more software-oriented things, but have much less and stumbled across much bigger problems in the physics-related areas. Yeah, in our earlier publications, we were talking about the so-called SMO tool chain. Yes, there is an existing tool chain with what we use for the embedded controller design, which is linked to the lump parameter dynamic specification of the controller dynamics, and then going through on a suite of refinement toward generating the code for the embedded controller and mapping it into a time trigger platform. We use for that time trigger platform. And one of the ongoing work actually is to change the platform now from time triggered also to canvas based, more event triggered that allows also event triggered operations. Yeah.
First, I would like to ask if you are also aware about tool chain approaches from other projects, and how would you compare? And I'm thinking especially here in Europe about things like projects like CESAR, latest IFEST.
Yeah, so we are totally aware of it, and we've been communicating with them. Some parts of that team were part of the early part of the competition also. So yes, they were in the competition until 2011.
How would you compare them with these approaches, basically taking the tools and just sending information, sending inside tool information on something like open space, open technical space, which could be interpreted by the other?
Right. So indeed, perhaps one of the bigger differences that because of the nature of the program, we had to very heavily focus now on the on physical behaviors and physical behavior composition. We don't use from the very beginning this whole contract-based design approach, simply because of the very heavy impact of acausal modeling in the physical interactions. We also understand quite a bit the difference between the FMI-FMU based model integration or simulation integration of what we use here. In fact, we use both. But all of that is rooted in the S-function interfaces network. So it's but the FMI-FMU is not going into that level what HLA does with the distributed simulation and the actual time coordination. So we are completely aware of it, what's going on, and and we are communicating with folks who are involved in that.
Last question.
Okay. Did you get the control system parameters, for example, state space controller parameters, for example, for coupling the engine and transmission systems? You need these type of parameters for dynamic modeling. Did you get from the engine manufacturer, or you're trying to extract these type of parameters?
Right. Wherever we can, we get that from the manufacturer.
Always you got it?
Not always. Not always.
Okay, not always. Did you try to reduce the number of parameters by dimensional analysis, pi Buckingham theory?
No.
Never?
No.
Okay, thank you.
Okay, let's stop here. Next session.